Oh, okay. Starting the recording. Um, so yeah, today we are just looking at um, making our what we've just looked at is making our buffer example work and fixing up some allocation issues and just a little bit of like MISC stuff, getting the buffer record copies working. Um, and now we're looking at getting our uniform example working. So we're going to update it to the new style. We'll get rid of all of this init stuff. So we'll get rid of all of that. Um, we'll go ahead and add the validation layers and the render doc capture layer. It's useful to have them both. We'll upgrade the Vulkan API version because we're using some new synchronization features. Yep, and here we create the renderer. We don't worry about this stuff. Gonna load our vert shader and our fragment shader. We'll just get rid of all this because, and we'll, yep, start again. So copy over things that haven't changed. Yeah, I think that lines up. So just like our buffer example, we've still got a square, so that doesn't really change. Um, what is going to change is that we're going to make a render path layout and make our subpass. But with our subpass, we're going to modify it. So still got shader stages, but we're also going to describe descriptors. So none of this changed. All it's changing is we're going to add a descriptor set layout binding. So we're going to tell kind of our program or our renderer what we expect this sort of subpass to look like in terms of descriptor sets, which are kind of our uniform binding points. Um, and the renderer is going to look after it for us. Look after making those descriptor sets, allocating them, and then routing to them. So we're still going to need the start time that we use to calculate the like spinning disk. Um, and we can copy most of our drawing codes from how it was before. So we'll get rid of this line here. So the indentation's correct. Cool. So the render step, we're going to get the current time so that we can compare it with the start time. We're going to submit. We're going to allocate our uniform buffer just like before. Then we can write directly to it. We get the new uniform buffer data. So we get some new matrices. We're going to write new matrices directly to that buffer. And then not have that. We'll make a draw call, just like a buffer example. Now the only difference is that we are specifying the uniform buffers to bind. Cool. So here we're just saying the uniform buffer offset 0 of this size. And the uniform buffers line up with the descriptor sets. So in this case, we've got a list of lists. So this is descriptor set 1, and these are the bindings in it. and this buffer will be bound to descriptor set 1 or descriptor set 0, the first descriptor set, I should probably say. But if we were to compile that, what have we done? Do notation in pattern. Probably our indentation's off. Classic. Yeah, there we go. This and everything after it. Try that again. Okay, so there's a few things that don't exist anymore that we've changed. So let's get rid of them. We don't need that. BSL. Yes, okay. So yes, draw uniform buffers doesn't exist. So when we go to our render types, let's add that. Draw uniform buffers, and it's a list of handles to buffer. So that should work now. Oh, just give my Haskell language server a minute. Mm, come on. Well, looks like we'll... Oh, yeah. Oh. So yeah, this shouldn't actually be a handle to buffer. It should just be buffer. Because like the user's creating it immediately. Descriptors, it's going to be, instead of being descriptor set layouts, it's going to be a list of descriptor set layout binding. So instead of the user creating the descriptor set layout, we're going to create it for them and put it into the subpass. So subpass set layouts. Okay, descriptor set layout. And then finally, yes, size. Um, yep, that's going to affect a few things, but that's okay. So in render, let's fix those issues. So when we acquire a subpass, Oh, we're going to put this on a few lines so I can read it a bit easier. Got device, subpass info, list of shaders, render pass. Yep. And let's make our set layouts on behalf of the user. There really is just like so much going on in Vulkan. It's nice when we can do some things kind of on behalf of the user. Cool, so instead of getting the descriptor set layouts from the subpass info, we've created them so we can just chuck them in. And then when we return the subpass in the end, we'll just add the set layouts there. Cool. And we've also changed the type of buffer. We also want to include the size. It's just going to be useful later. So what else do we need to change? Okay. Need to import with VK descriptor set layout, I think. Let's get my Haskell language server up. Hey. And give it a minute to get started. Can't wait for the Haskell language server to be a bit better. Okay, that's not working. Alright, let's just add it manually. There we go. So, I'm going to grab the pipeline layout and the set layouts. Instead of ignoring the descriptor pool when we get the framing flat, which is here, we're going to grab the descriptor pool because we're going to need to create some descriptors. We're also going to pass the swap chain into the submit function because we need to use the swap chain information sometimes. So when we get drawers, we're going to pass in the swap chain. Cool. And yes, so draw vertex buffers. We're going to have an issue here. Going to ignore the size. And when we draw index buffer, yep, same thing. Now we're going to create a new section. So before we make the draw, we're going to allocate some sets. So we can actually copy this from, we've had this code before. So yeah, we allocate descriptor sets for each set layout. This gives us something to write our descriptor sets to. And we go like, actually, we should probably go unless null set layouts. Because if there's no set layouts, then we probably shouldn't allocate anything. Probably is an error. Cool. So we've made our sets. Let's make our writes. These are the descriptor set writes. So just like flip, fold map. Oh, should I do that? Sure, why not? Okay. I'm gonna zip the sets with the draw uniform buffers. So we've allocated a set for each descriptor set layout, and then the user's bound a buffer to each descriptor set layout. We're gonna zip them together. We might get something more complicated in future, but this will work for now. So then we've got the descriptor set, buffer, and the information about the buffer. Let's indent this a little better. Cool. And then we're just going to say write descriptor set and fill in this information. So we've got our chain, which is just nothing. We've got a destination set, which we'll be writing to. Destination binding, which we'll just say 0. Destination array element, just say this is 0. And if we need to change it, like if we need to use those things in future, we'll come back to it. Gonna make sure that we approach this iteratively so we don't get overwhelmed. Uniform buffer. This is the image info, which we're not using. And now we're going to specify a buffer info. In this case, it's a single buffer. And again, you're going to notice some deficiencies here. Like, what if we want to have multiple set layouts? Well, you're right, it won't work, but we don't have multiple set layouts at the moment. So it's going to work fine. And when it breaks, we'll fix it. This is the Texel buffer view. Sorry, I'm just reading documentation. This other screen. I do not know these off by heart. Cool, so that's our write, and then we've got our list of writes. Now we should write those writes. So lift IO, VK update descriptor sets, pass in device from the context. We have to do this really dumb thing, but we're just gonna basically pass in our writes, and this is some copies which we just leave empty. So now we've written our descriptor sets, we should just bind them. So we've written to them. It's the graphics pipeline bind point. Got our pipeline layout. This is the first set. And here's our list of sets. So this is sort of like an offset argument, which we're not going to use. And then this is like dynamic offsets, which we're also not going to use. What's wrong here? Oh. Indent. Cool. So we'll only do this if we have set layouts, and essentially we have, for each set layout, we've allocated a descriptor set to write to. We've made our writes, we've then written them, and then we bind them. So write just tells us what buffer is bound to what descriptor set. I have to change the type signature of our draw function. Let's try and make this a bit more readable. So this is now a function from swap chain to draws. Cool. Now we've broken our buffer example, but that's okay. Go fix that. Okay, need to import some things for our unit form example. Oh. So we're just importing these functions. Cool, that's working. There we go, we've got our spinning disk back. or a spinning square. Let's get rid of those warnings. Let's fix our other examples. So for our triangle example, let's add our validation and render dark layers. Okay. So descriptors, that's fine, but draw uniform buffers, we'll need to initialize that. And now our submit function takes a swap chain, which we're not going to use in this example. So we should be able to load our triangle example now and run it. Cool. There we go. And we will do the same for our buffer example. It's all good. Descriptors is all good. And again, we're not using the swap chain here. So we'll just do that. There we go, buffer example is working again. And we'll just check for any warnings. Nope, all good. So, we'll call this, just go through, review what we're doing. Working uniform buffer. I think that's all we need to do. Cool. Oh, hang on a sec. Examples. Oh, okay. Never mind. And just looking at my notes. Yep. So I think next we'll work on a texture loading example. But right for this minute, let's go and make that texture example. Yep. So for the texture example, we'll just copy the uniform example and we'll add a texture somehow. Texture. Texture. All right. For now, I'm going to take just a 10-minute break and we'll be right back. Okay, I'll see you guys soon. Alright, welcome back. Okay, so we got our uniform buffer example working, and now we are looking at getting a texture working. Um, so let's create a new vertex shader and a new fragment shader and have a look at what that might look like. So data texture dot vert. Done. Okay. Sorry, give me a sec. Okay. So it's going to be very similar to our uniform example where we've got our uniform buffer. Um, we are going to slightly change our inputs. So we've still got position and color, but we're going to add a texture coordinate, which we can use to sample the texture. And then we're going to output color still, and also the texture coordinated, like interpolated over the fragments. Um, the position is going to be the same. The frag color is going to be the same, but the texture coordinate is going to be different. It's going to come from this in texture coordinate. Cool. And our texture.frag, that is going to take the frag color and the frag texture coordinate in, and also a sampler, like the texture, a sampler to an image. And we're going to output the color that we output is going to be sampled from the sampler at that fragment's texture coordinate. So we'll just compile these. Cool. And we'll use them here. We'll add this texture example in. Okay, so we're going to need some way of allocating an image using our allocators. At the moment, we only allocate buffers. We're going to need some way of binding the image, just like we did binding the uniform buffers. So that's going to be a little bit different. We need some way of loading the texture. Yep. And yeah, I think that's it. So let's start with loading the texture. Let's add a little function here that takes a file path. And it's going to produce an STB image. So it's going to use the STB codec. So we're just going to presume there's like 4 components and we're going to load the image. It's not a great texture loader, but it doesn't matter. And then, in terms of our texture example, we probably want some way of loading a texture. And imagine that would look something like this. So we want some texture, we'll just have the same sort of format. We'll get the image data. So we've got the image data. Get the size of the image data. And then we'll just probably return some sort of texture info. Uh, 8, I think this, yeah, this texture, this format is suitable. So yeah, we're kind of hard coding it for this specific texture, but that's okay. So yeah, we'll pass in the format of the texture, the width and the height, the size of like the size of the data, and then the data itself. Just import this word 8. And with bitmap, that comes from bitmap. And we're going to load the texture. Lift.io, load texture. Okay. So let's have a look at this tab. Texture info. So, just add it at the bottom here. Texture info A. It's going to be a lot like the buffer info. Got a format. VK format. We have a width. Width, that's how you spell it. Height. Size. And then the data itself, which we kind of take as storable. But we won't put the storable constraint here, we'll just put it wherever we use texture info. Oops, I've named that incorrectly. Cool. And data texture. So the final texture we make is going to be like the VK image, the image view, and the sampler. VK.sampler. That should be kind of like our texture. We'll need to add a texture handle. So it's deferred computation from so for all x, here's where we put the storable x. Go deferred computation from some sort of acquire texture info to texture and handle texture. So kind of pinging around the design space a little bit with this whole like deferred computation stuff, and I think it's going to change even more in future. Yeah, but you know, we'll figure it out. The thing is that here, in order to like figure out what the format is, you sort of have to load the texture first. So I couldn't do something like with the buffer where I just said, oh, this is a vertex buffer. I kind of have to look at the texture and then decide the format afterwards. We'll figure it out. This will do for now. Okay. And yep. We'll import text info. Oh, will we? Looks like we'll just crash Haskell language server. We'll just import it manually. Okay, and in render, we're gonna have to do implement this whole texture thing. So buffer, render pass layout, subpass. Let's add another one. Texture. So give a renderer and acquire texture info A, storable A, then go back, handle to texture. Cool, so we've got our info, we've got our renderer, and simply go texture handle, defer info, import texture handle. Then we need some way of evaluating the texture. Eval texture, UK context, renderer, handle to a texture, and we give back a texture. So context, renderer, texture handle, eval empty, it's a lot like our buffer example. All right. This is pretty involved, so I don't want to bore you guys with this, but let's go through it. So we're going to first create the image. Oh, I should probably get the format from the image. There we go. We create the image. We're saying it's a sampled image and that we're going to copy to it. Because just like the buffers, with images, we're very likely to get a staging allocation, which means that we need to manually copy the data to the image. So we've got this pretend with image allocation thing. We're going to poke the data and flush the allocation. And just like with our buffer example, we're going to see, does this require a copy? And if it does, then we're going to write to the pending writes queue. And instead of a buffer copy, we're going to have a buffer image copy. So with a vertex buffer, we've got a buffer to buffer copy, but with an image, we're copying from buffer to an image. So we've just got slightly different parameters. So you can see here we're copying a buffer image copy, or using a buffer image copy as the region. Then we're going to create a image view to view the image and a sampler to sample the image. Then we're going to return the image itself, the image view, and the sampler. So let's look at this buffer copy. So instead of just having one type of copy, we're going to add another type of copy, and it's going to be called buffer image copy. Oh. What's the thing for that? Duplicate record fields. Okay. And we're going to unify these two types in a single type called buffer copy. So we can either copy to buffer or copy to image. And then we're going to change this render appending rights to buffer copy. And we're going to create a function called record copies. So record copies will take a list of these buffer copies and split them between kind of our two buffer copy recording functions. We've got buffer to buffer and buffer to image. Need to add a lambda case. So we need to do the buffer to image copy. So we've got our record buffer copies. Let's implement that function. Record buffer image copies. So it's going to be very similar to the other function in terms of type signature. It's going to take a list of buffer image copy infos. And it's going to return nothing. So just like before, if we don't have any copies to do, we will just do nothing. But if we do have buffer image copy infos, we'll do something. So we need to make some mem barriers. Yeah, okay. This is going to get a little bit involved. So we have to make a image range. So what range of the image to copy? In this case, we're mostly just gonna, well, we are just gonna hard copy this, and as we need more functionality in future, we'll revisit that. It's just a good way to go, kind of iterate. Otherwise, there's just like too many Vulkan options. Like it's just too overwhelming to try and abstract it all well. And then pre-copy memory barrier. So we're going to have two different memory barriers, one before we copy and then one after we copy. So when we were doing the buffer to buffer copy, we just copied the buffer and then we added a memory barrier afterwards. But with images, we're going to need to do two. And so one is going to like transform the image layout from undefined, which is kind of how the image starts, to an image layout that's good for transferring to. Then we're going to transfer to it, and then we're going to change it from transfer optimal to read optimal so that we can read it in the shader. So image memory barrier 2. We've got the chain, which is nothing. We've got the source, stage, mask. Source, access, mask. Then we've got the destination stage mask to transfer bit KHR, and we've got access to memory bit destination access mask. So I'm not quite sure how to interpret 0 here, but it's kind of like um, don't write anything. Actually, I'm not sure. I'm not even going to try an attempt. But here's the important part, which is where we're going to change the image layout. I'm not bad at reading these source stage access stage masks. If there's like both of them, but there's only one of them, I get a little bit confused. Don't really care about the Q family here. This is the image we're going to be putting this barrier on. This is the range. Okay. So we're going to create one of these barriers for each image. Then we are going to set up our dependency info. So we're going to make a call to the pipeline barrier, and we need a dependency info struct to do that. So you can basically just ignore this. It's just a way of passing arguments in. Vector.empty. Let's go to dependency flags. We've got our memory barriers, which is what we used before. Got our buffer memory barriers, which we haven't used yet. Then we've got our image memory barriers. There we go. And then we just need to pass that into command pipeline barrier to KHR, command buffer dependency info. Probably haven't got the alignment right yet. Oh no, we're good. What's on? Maybe I do. Do let. It's also part of the let. Oh well. Cool, so that's our pre-copy. Then we'll do our copies. So we added a pipeline barrier essentially to transfer our image layouts to something we can copy to. Then we're going to actually copy. Oh. And that's going to be command copy buffer to image command buffer. And then copy.source buffer copy.destination image. And then image layout transfer just optimal, and then the regions to copy. Cool. So we've got our copy. Now, we've got to do our post copy memory barriers. And that's going to transfer our image layout to read-only optimal, which is good for sampling, which is what we need for this texture because we're going to be reading it in the shader. And the way that we do that changes based on if we're using a unified graphics and transfer queue or using like multiple queues. And like I said, it's complicated if we have multiple queues. So we're just going to ignore that for now. So if they're not the same, I'm just going to say something like separate transfer and graphics queue, not for buffer image copy not implemented. All right. So similarly, we are going to have an image range and uh, actually going to have some memory barriers. Post copy mem barriers. Post copy mem barrier. Post copy mem barrier. Let's there we go. So same as before, the image range isn't going to change. This is going to change. So we're going to wait for the transfer to be written. So essentially going to wait for the data to be written. So we say transfer bit and then transfer write. And once that's done, then we can shader read the fragment shader. Fragment shader bit khr access to shader read bit. So don't read from the fragment shader until we've written the transfer, which makes sense. It's like we don't read from the image until we've written to the image. So the old layout was transfer dist optimal, and the new layout is read only optimal. So image layout read only optimal. Because we've copied to it, we're not going to need to copy to it again, at least not right now. We're going to want to read from it. Cool, so that's our post copy memory barrier. And then we create another one of these dependency info structs, so we can just copy that. Except the mem barriers now are post copy mem barriers. And post copy dependency info. There we go. There's our second pipeline barrier. Let's call this pre-copy, just to keep things consistent. And pre-copy memory barriers. Okay. Let's load this. Gonna have a bunch of areas, but figure it out. The last statement in a do. Oh. Yeah, this shouldn't be a do. Wonder if I can get rid of this now. Cool. 131 command buffer not in scope. Yep, that's an issue. Yes, okay. So it looks like when we're writing to the buffer copies, we need to make sure to record copies instead. So just changing the type of the queue. Well, we have changed the type of the queue, so we need to make sure that what we write to the queue makes sense. So any buffer copies, we're going to put a copy to buffer around it, and any image copies, we're going to put a copy to image around it. Okay, so we're missing a few Vulkan tools. We haven't visited that in a while. So we've got our Vulkan module with just a bunch of things that we need to create. These are kind of like the raw Vulkan calls that we've wrapped in we've wrapped in acquire from the resource T package, just a way of acquiring these resources. So we need to add a couple more, sampler and image view. Now, I've made these before, so I'm just going to copy them because they're not that interesting. All we're doing is wrapping for sampler, for example, we're wrapping a call to create sampler and destroy sampler in this kind of like bracket function. And now we can go to render.hs where we use with sampler, and what is going on? File texture. Huh, weird. Alright, get rid of that. Looks like my Haskell language server crashed. Give it a restart. It's always good fun. Come back to me. Okay, it's broken. So that was an issue with render types. Texture. We'll add with image view and with sampler. And with image. Oh. 581. Oh, that's from the allocator. Never mind. Yes. Cool. So the other thing is that we don't have any way of allocating an image using our allocator. So we've got a way using our buffer, but not images. So what we're going to do is we're going to change this type to include, actually, yep. To include kind of indication of what the allocation is referring to. So is this a buffer allocation? Is it an image allocation? Is it something else? So if we get device allocation, it's just whatever we've tried to allocate. And if we have a staging allocation, the device allocation is whatever we tried to allocate. But the staging allocation is always a buffer, at least in our current case. So in the case of a buffer to buffer, we've got a buffer here and a buffer here. But if we create an image and it gets the staging allocation, which means that we've got a device allocation of an image, but we can't write to it directly. So we've also allocated a staging buffer for us to write to that we'll then copy over. The staging allocation is always a buffer. Even when we allocate an image, we need to copy the data to a buffer and then copy the buffer to the image. So it's not like we have a staging image. We have a staging buffer, which we copy to the image. So in this case, the allocation is going to be of type buffer because it's a buffer allocation. This function doesn't care at all actually about what the type is. Nor I think does flush. Could be wrong. Sorry. Just refer to my notes. Yep, I don't think it cares. We'll call this get alloc data now. Whoop. So it'll just return whatever type we allocated. Don't care about that. Okay, so requires buffer copy, that's going to change. Yes. So requires buffer copy is going to return either, it's going to return staging buffer and then either the buffer or an image depending on what type of allocation it is. So then we can create an image allocation function. So we've got our image create info, we've got the size of the allocation, and then we're going to return this acquire type allocation bk.image. So in a lot of ways, this is going to mirror our buffer creation function. It's going to be very similar. So alloc create info. This is a Vulkan memory allocator structure. So vma dot allocation create info. Start with the flags. What have we got? So allocation create host access sequential write bit. So it means like we want to be able to write to it from the host, which is the CPU, us. We want to, but we do want to give it the option to allow transfer instead, where it creates the device allocation, we create a separate staging allocation, and then we transfer it over. And we also just want to allocation creates mapped bit. I'm not sure I've seen a case where it's given me a device allocation. I think it always gives me a staging allocation, so I don't know. It's maybe not the best way to do it. And everything else we can just copy from our buffer. So memory usage auto, so just let it decide memory usage. It's usually the best option. Okay, now we can actually allocate our image. So vma create image, allocator create info, alloc create info. Then that's going to give us image allocation info, and we'll destroy the image at the end. So essentially we're telling it how to create the image and how to destroy it, but we're not actually doing either of those things yet. It's only when it's used that we'll do that. So then we're going to get, just like in a buffer example, we're going to get the allocation memory properties of the allocation. and we're going to check if it's host visible. So if it's host visible, we can write to it directly, which means that we don't need a staging buffer, which means we return a device allocation. Otherwise, we're going to need to create a staging buffer. So that staging buffer create info. Buffer create info. I got some indentation issues here. Alright, so nothing for the chain, nothing for flags. We'll create a buffer the size of the image. We'll say it's a transfer source. What's used as a transfer source? We don't care about sharing at the moment because we haven't implemented multiple queues and we probably won't. Our staging allocation create info is going to be very similar. Except we're not going to allow transfer instead. We're just going to ask for something that's host visible and we're going to map it. And then we can just copy this from our buffer part where we create a staging buffer and destroy it at the end. And we can return our staging allocation. So we've got our staging buffer and then we've got our image, our device image. And there we go. That's our with image function. Go back to our renderer. Go back to allocator. We'll go with image, import that. And get alloc buffer is now get alloc data. So anywhere that's used, we'll replace. And looks like I've made a mistake. Okay, that's pretty simple. Yep, okay. Some interesting errors there about types. Yeah, okay. What do we usually have? Start with monad resource. What else do we need? Monad mask. And monad unlift IO. Okay. 71. Import texture. You have a question about your PC? Do you think I could help? Yeah, I mean, fire away. We'll give it a go. Okay, so it looks like so we've made our texture. We've dealt with the whole idea of copying our data over to the device. But what we haven't done is find a way to bind our texture. So we're going to add a descriptor set binding, descriptor set layout binding. So once we do this final step, we should have a texture on our little spinning disc. So, well, if we have a look at our fragment shader, can see that at binding 1, we've got our sampler. So binding in shader, the type is not uniform buffer, it's descriptor type combined image sampler. The count is 1, and the shader stage is shader stage fragment bit and no immutable samplers. Okay, so you just built a new PC and it all works fine, but it won't go up. No, don't worry about it. I like questions. It's been so long since I built a PC though. No bootable devices. And your hard drive already has Windows installed. I mean, I remember having an issue and it had something to do with my RAM. Like the RAM wasn't plugged in properly because like it required quite a bit of force. I don't know if you checked that. I know it doesn't sound anything like it would have that kind of effect, but I've had that problem before. Um, let's have a look. So yeah, check your RAM setting. Okay, okay. Oh, thanks, Sam. Yeah, I mean, check. I don't know. Give it a Google. See if you can find something. Check in your like BIOS to see if there's any like if you like press F12 or whatever to go into your BIOS, see if there's any bootable devices listed. Um, yeah, I'm sure you'll figure it out. Mm. All right. Oh, that's cool. Well, come back and let me know how you go. See ya. So, we're gonna make a few different changes. Like, we've changed our vertex inputs, so we've got like texture coordinates now. We're gonna have to add. So, what are our texture coordinates? 1, 0, 0, 0, 0, 1, and 1, 1. Oh. So, we've got our position in the first two, and then we've got our vertex color, and then we've got our texture coordinates. Just the different sides of the square, corners of the square, rather. Um, so now you can see that each vertex is made up of 7 floats. So we're going to change the size of the stride to 7. And then we've got a new vertex input attribute. We've got position and color like before, so that'll stay the same. But then we've also got text coord, and that is 2 floats. So we'll use that format. And it's 5 floats in. It's the last 2, so 5 plus 2 is 7. What were we doing? Oh yes, we need to bind the descriptors. So bind the texture to the descriptors. So we're going to change uniform buffers. Because they use the same system, we're going to change it to descriptors, draw descriptors, and we'll have like something like descriptor uniform, and then just the information we had before. And we'll have descriptor texture. And because we might have multiple descriptor sets, we'll make it a list of lists. So this will be descriptor set 1, which has 2 bindings, which follows this same thing. So this is also a double list, with the first list being the list of descriptor sets, and this being the list of bindings in the descriptor set. So we'll just like zip the two together so that they match up. But yes, we're going to have to go to our render types and go to draw uniform buffers and rename that to draw descriptors. And instead of being a list of buffer, we're going to create a new type called, what did I want to call it? Draw descriptor. Draw descriptor. So we've either got our descriptor uniform, which is going to be the buffer that we had before, but now I've got a new type, descriptor texture, and that's going to be a handle to a texture. And we'll call that draw descriptor. Not in scope. Oh, ignore that. Cool. So now we just need to change our render thing, our render module. So draw uniform buffers. So now draw descriptors. And I don't think we'll need to change the allocate descriptor sets, but we are going to have to look at each of the descriptors and decide on its type. Decide based on its type what to do next. So, oh, we've got a list of lists now as well. Okay. So, this is fine, but we're going to change this to descriptors, because remember, so we changed this to a list of lists now. So descriptors, and then I'm going to do another kind of inner loop where we zip each of the descriptors with an index. That's going to give us index descriptor. We'll just put that on a new line for consistency. Let's just yeah, that'll do. Then we'll go case descriptor of if it's a descriptor uniform, buffer, buff, offset size. We'll just do what we did before. But if it's a descriptor texture, we have a texture handle, then we're going to do a get to get the image view and the sampler from the handle. And then we are going to, so we're going to actually need to make this monadic. So we're also going to output a descriptor set, right? But it's going to be slightly different. Oh, we should put the index in here. That's why we got one in the first place. Descriptor count, uniform buffer, buffer info. Yep. So this is very similar, except it's now combined image sampler. And in the image info, instead of it being empty, we'll make the buffer info empty, and we'll make the image info a singleton, and descriptor image info, pass in sampler, the image view, and the image layout. So we transferred our image layout to read-only optimal by this point, so we can just presume it's in that format. And that's it. Now what's going on here? Looks like I didn't change the type. Yeah. There we go. So these rights, they're now a monad. So we can bring this in a couple. Yep, we're going to need to 4M this and 4M this. Does anyone know a better way to do this? So I'm like wanting to like use 4M over the thing and then concat the results. I'll just do this for now, but I wonder if that's enough. No. Made a mistake with my shader. Ah, just a little one. Deferred value not yet evaluated. Yep. So we've got a bunch of deferred computations and we need to evaluate them. So when we evaluate the buffer afterwards, we can be like, let textures equal. So we'll get all of the textures and uniform, the descriptors basically, used in the draw. And we'll, if it's a uniform, we actually don't need to do anything because it's not a deferred computation, like there's not a handle. But if it's a texture, then we'll return that. And actually, what am I doing? We'll iterate over and we'll just go pure nothing. Otherwise, we'll eval the texture. There we go. So we've got a texture appearing on the disk, on the spinning disk. So I'll just fix up some warnings that we're getting here. So 96, not using that. 579. Just check for any other warnings. Ah, yes. So we've changed the structure of our API, so we're going to need to fix our previous examples. So there's no draw uniform buffers anymore, it's just draw descriptors. I think that should be enough of that. For our buffer example, the same thing. Draw descriptors. And for our uniform example, that's fine. Same thing, draw descriptors, but we'll have a double list. And we'll call this descriptor uniform. Import that. We'll reload our examples. Okay, let's load our triangle example. And our triangle's still working. That's good. We'll load our buffer example. There we go, our buffer's still working. And then we'll load our uniform example. We've got our spinning disk. And finally, our texture example. Cool. So, I think that's it for our texture example. Sorry if there's any lag. Looks like my computer's dying. Just checking my notes, see if there's anything I missed. Okay. All good. So yeah, we've got a working texture example. We've got a kind of like decently high-level interface to describe how we want our resources to be loaded, then to describe the render pass itself, and then to make some draw calls with that render pass. It's not perfect, but we're building it iteratively, so we'll hope it gets better in the future. So let's make sure that I've committed everything we need. Texture.vert, texture frag. Okay. Working texture example. So for those of you who don't already know, can follow along with the commits at github.com/SamBennett/RORT. RORT. So SAMBNT/RORT. So you can see our working texture example just then, so you can follow along live. And then I'm uploading these streams to at Sam Bennett, SamBNT_TV. You can see all of the previous streams there. There's a playlist for it. So I'll be uploading this video today. Okay, so I think next we'll move on to a depth buffer. But for the minute, I'm just going to take a quick break. Um, Gotta take breaks. So I'll just take a 10-minute break and then I'll be right back. Thanks for watching. Okay, we're back. So, we've just got a little bit of time left in the stream. So let's try and get started on our depth example. So we'll just copy our texture example and we'll call it depth. Change what we need to change. We'll add it to our example list. Let it up. Cool. Just looks just like our texture example for now. But let's draw another square on top of it. And we'll see how the depth buffer works at the moment. So, we've got our square 1. Let's make another square. Negative 0.5, negative 0.5. Let's add a z-axis. So, what we'll do is we'll add the z-axis first. So we'll position this first one at 0, 0 height. Then we'll make another one. Same square, but it's going to be positioned at height minus 0.5. So a little bit below the existing one. Just align them nicely. Okay. And then we'll call these new vertices, or give indices for these new vertices so that we can draw them. We're going to have to change our, we've got 8 floats now for each vertex, and the position is now made up of 3 elements. So we'll add that third element into the format there. The index buffers, they're still word 16. What else do we need to do? We should make this the length indices. Change the number type. I think that's all we need to do. Let's give that a go. No, we're still only loading 1. Why is that? I think I need to change my vertex shader. I think we're drawing both of them, they're just being drawn on top of each other. Because in the vertex shader for the texture shader, the texture vertex shader, the in position is only 2 vec2, and I think it's just ignoring that third element. Oh, hang on a sec. Something's happening in my house. Sorry about that, my pressure cooking cooker going a bit crazy. Yes, so let's copy this and make a depth. Data depth dot vertex shader. And it's going to take in a vec3 position. So we can get rid of this. Then we'll compile that. Depth.vert to depth.vert.spv. Reload our depth example. And there we go. We've got our two squares rendering. Now, because there's no depth buffer and we're not doing any depth testing, the lower one is rendering on top of the upper one because it's coming second in the render order. I think we can switch that around if we change the order of the vertices that we call. Yep. So this is kind of what we want it to end up as. But ultimately we don't really want to have to order our draw calls by the depth, like how far away they are from the camera, because that's fairly inefficient. So we want to be able to draw in any order, but make sure that our whatever's on top is on top. To do that, we can use a depth buffer. Cool. So we're back here. So let's commit this. And we'll call it motivate depth buffer. So we have a reason to create a depth buffer. So what we're going to have to do is sort of rework our API here, our renderer API, to specify the layout, the images that are attached to the render pass. So at the moment, this render pass layout doesn't actually take any arguments. It's just kind of a skeleton. We're going to have to change that to take the images that we want to attach to the render pass, the images that we're going to render to, because we need to render to a depth image. Yeah. Now it's going to be a fairly involved process. So I think we'll end the stream here for today, and we'll come back to that next stream. But yes, I imagine that we'd create a render pass, set up the attachments, specify the subpasses that are going to use the render pass, and then we'll probably change our draw call to specify the render pass that we'll draw with. Yeah, we'll just mimic the Vulkan interface, really. We're not trying to abstract Vulkan too much. We're just trying to make it a little bit easier to use. So I'm just having a look through my notes, and I'm seeing if I mixed anything. No, okay. So yeah, so next stream we'll figure out how to specify attachments to our render passes, which is going to get us a long way to doing things like deferred rendering. And I think after that, we'll have a look at loading models so that we can start to get some cool things into the rendering engine. Yeah, so I'm looking forward to that. So thanks for listening today, and I'll catch you guys next time. All right, have a good day. See ya.